Thank you. First of all, I want to thank Alexei and all organizers for the invitation. This is the first time I participate in this very interesting series of workshops, and moreover, this is the first time I visit Armenia, so it's a double pleasure for me. In my talk, I plan to speak about some applications of complex analysis to operator theory, spectral theory of linear operators. But let me start with a very simple thing that everybody knows, everybody has met many times. So these are interpolation formulas where we interpolate at zeros of some fixed entire function. So let G be an entire function with simple zeros, number n, and then for some entire functions, we may hope to have such a representation as in this interpolation series. Yes, we interpolate and knowing the values of the function at the points number n, we can recover this function. Of course, there are many questions. The series must converge. There are some conditions. Not even if the series converges, it's not clear that it represents our function, because probably there is something which just vanishes at the points of the zeros of G. So it's more complicated, but for some classes we can have such interpolation formulas. For example, a trivial example, of course, if G is a polynomial and F also is a polynomial of degree, a smaller degree, then it's a standard interpolation formula for polynomials. Another classical example is the Peli-Wiener space. Peli-Wiener space, it consists of all entire functions of exponential type at most. We fix here the constant pi, which are square summable on the real axis. In other words, these are Fourier transforms of L2 functions with the support in the interval from minus pi to pi, the so-called band-limited functions. And then we have the famous Shannon-Kotelnikov-Whittaker sampling formula, which again recovers our function, our signal from its samples, its values at integers. And this is this formula. And this function sign, of course, we can take it out of this sum, and then we have this representation. And this series, it converges both uniformly on compact sets of the plane and in L2 norm, moreover, it's an orthogonal series. And some more general examples of representations of this type, they appear in the theory of the branch spaces of entire functions. I will mention the branch spaces a bit later. But now the main idea is let us consider the class of functions which can be represented in this way with some additional restrictions on the samples, on the values at the points, and let us define some class of spaces of entire functions using this idea. So here appears the spaces of Cauchy transforms that are in the title. We define them as follows. So we have the following three parameters. First parameter is the set T, the points Tn. They are complex numbers, not real, complex numbers, which tend to infinity. So there are zeros of some entire function. And another free parameter is the measure mu, or the sequence mu_n of, so to say, masses, which are assigned to these points Tn, with only one restriction, that this series converges. Well, and then with each such pair, T and mu_n, we now associate a space of entire functions. In fact, we add one more parameter. We fix some entire function A, which has zeros exactly at these points Tn, and no other zeros, just only simple zeros and Tn. And then with this triple T, A, and mu, we associate the following space of entire functions, which I denote H, T, mu. And this is, by definition, the space of those function f, which can be represented as the following series, where coefficients Cn, they are square summable. Of course, this condition, it ensures that this series converges absolutely in uniformly on compact sets. Very well. And so we consider this class of functions which admit such representation. And we define the norm on this space as the norm of the coefficient Cn in L2. So everything is defined by these coefficients. So essentially, it is the space of discrete Cauchy transforms, and then we simply multiply by this function A to get a space of entire functions, to get rid of these poles. But I deliberately do not mention A as a parameter of our space, because of course you can say we can choose many different functions. A multiplied by exponential, you have another function. But essentially, all these spaces will be canonically isomorphic. There will be nothing interesting in the structure of the space, which if you multiply here, the function, all elements of the space are multiplied by the same function, which has no zeros. So A is essentially, it's uniquely defined, more or less uniquely defined by the zeros. So indeed, three parameters are indeed T and mu. So this is the main object that I want to speak about today. So, and again, if we recall this example with the Pedi-Wiener space and the Shannon-Kotelnikov-Whittaker formula, of course, it's a special case where as t we take integers, as a we take this function, sine by z, and um, these masses are identically 1 in our case. In this case, our space is just the usual Pedi-Wiener space. So, what good properties this space H T mu has? What can we say about this space? Let's see here, just recall its definition. And then, obviously, it consists of entire functions. It's a Hilbert space. It's easy to verify. That's this norm. This norm is a Hilbert space. And moreover, the H of T mu is a reproducing kernel Hilbert space. What does it mean? It means that all evaluation functionals for any W, complex number, this is a continuous functional in this space. Therefore, of course, it's generated by some function in our space, reproducing kernel, KW. So it's a reproducing kernel Hilbert space. And the second nice property is that this space has the so-called division property. We can divide out zeros. If we have a function in this space which is 0 at some point w, then the function f of z divided by z minus w also is in this space. This again is immediate from the definition. Moreover, if we look at these functions, which are the summands here, there's one summand, they correspond, of course, to the sequence of Cn, which has 1 at the position n and zeros otherwise. So such functions, they correspond to the orthonormal basis in the space L2. And so they form an orthonormal basis in our space, because our space is isomorphic to L2, its coefficient. The norm is defined in terms of the coefficients. But on the other hand, if we consider the inner product of this function f, we represent it as above with this function, we get the coefficient Cn, which actually is f of Tn up to some factor, depending on n, of course, up to some constant factor. So we see that these functions which form an orthonormal basis, they also are reproducing kernels exactly at this point Tn up to, again, some constant. So we see that our space, it has a orthogonal basis which consists completely of reproducing kernels, which is actually quite a rare situation. In the case of spaces of analytic functions, usually they do not have orthogonal basis of reproducing kernels, Hardy, Bergman, etc. It's never possible. But here it is the case, and conversely, actually these properties just define already the structure of these spaces of Cauchy transforms. Conversely, any reproducing kernel Hilbert space, which consists of entire functions, which has a division property, and which has an orthogonal basis of reproducing kernels, just one basis, it is automatically a space of the form H of T mu. That's not difficult to show. Okay. So this is the class of spaces I want to speak about. And a bit of their history. Well, of course, such representations, they are ubiquitous in mathematics. They appear in function theory everywhere. But just very formally, these spaces with the Hilbert space structure, the norm, they were introduced in the paper by Yuri Belov, Terence van Mengst, and Christian Say. 2010, and in this paper they studied mainly the questions about sampling and interpolation in these such spaces, and mainly they treated the case of very sparse, like unary, exponentially growing sequence T, where one can have a very explicit description or a very explicit solution of such questions, and then there were further results in this direction about sample interpolation by myself with colleagues from France, from Bordeaux, and later, jointly with Dmitry Yakubovich from Madrid University, we developed a functional model for rank 1 perturbations of compact operators. This is actually the main subject that I want to speak about today, applications of these spaces to the spectral theory of rank 1 perturbations of compact operators. Well, and another topic was the study of nearly invariant subspaces, which are subspaces invariant with respect to this division operation. We can divide out zeros, and we remain in this space that we did jointly with Evgeny Abakumov and Yuri Belov. And recently there were some rather unexpected connections of these spaces. We have some applications in time frequency analysis, in description of Gabar frames for some special window functions. I will not go into this today, but this is also a rather unexpected application. So as I said, I will want to just very briefly mention the so-called Lagrange spaces. So Lagrange spaces, by one of the equivalent definitions, is that these are reproducing kernel Hilbert spaces, which consist of entire functions, and have two properties. First, they are invariant under conjugation, when we pass from entire function f to this conjugate entire function, f bar of z bar. And the second property, it's more or less about division of zeros again. If we have some point w and the function f of w is 0, we divide by z minus w and multiply by z minus w bar. And this function must be in the space, and it must have the same norm as the initial function. So we can divide or multiply by Blaschke factors in our space, and this doesn't change the norm. So this is one of the definitions of the branch spaces. They were introduced by Louis de Branch in the 60s, maybe, and the 50s, and they were introduced in his solution of direct and inverse spectral problems for two-dimensional canonical systems. Again, I will not go into details here, but these spaces, they appear as the spectral counterpart of the canonical systems. What is the relation between the Lagrange spaces and the more general spaces that we consider? Actually, if our sequence is real, our sequence T, and the function A we also then choose to be real on the real axis, then the corresponding space is a Lagrange space. Well, it's very easy to verify these axioms, and conversely, again, any Lagrange space can be represented in this way. So these spaces of Cauchy transforms that we introduced, they are a certain generalization of Lagrange spaces. Therefore, sometimes we use for them the term Cauchy-Lagrange space to emphasize both the role of the Cauchy transform and their relation to Lagrange theory. So as I said, I want to focus today on the applications to the spectral theory of one-dimensional perturbations. So let me now discuss this in more detail. So simply we have a compact normal operator in a Hilbert space with simple spectrum, with trivial kernel. So by the spectral theorem, a just multiplication by z in some space with the discrete measure. So it's a very, very simple thing. We know everything about such operator. We know everything. And let us consider just very, very small perturbation of such an operator, just a rank 1 perturbation. So we took 2 vectors, A, B, from our space, and add this operator, which is, by definition, of course, is tensor notation. It means simply that we multiply f by b, take in a product, and take it as a coefficient at A. So a very, very small, very, very simplest perturbation in a sense. And then one can, of course, ask many natural questions. Which good properties of our operator L, which of these properties are preserved? For example, are eigenvalues and root vectors of L and of this joint operator L star, are they still complete? Which we of course have for the operator L, for the operator A, unperturbed. Does the operator L admit the so-called spectral synthesis? What it means for an operator to admit the spectral synthesis? It means the following. Assume that we have an invariant subspace M of L, and then the question is, can we reconstruct this subspace M only knowing eigenvectors and generalized eigenvectors which belong to this space? So can we recover any invariant subspace from the, so to say, spectral data? So the common question is whether M is equal to the span of these generalized eigenvectors which are in M. Okay? So if this is the case, we say that the operator admits the spectral synthesis. Well, and of course, also can ask for a compact normal operator, its eigenvectors, they simply form an orthogonal basis. Can we say that the eigenvectors of L, they form a basis, at least in some sense? So these are natural questions that one may ask, and more or less the answer in general, I want to say again that the answer in general is no. Already such a small perturbation, it may completely change the structure of everything. So in general, there is no general theorem which says that any of these properties is preserved. In general, it is no. And the key idea how one can study such perturbations was to apply a certain functional model which give you a unitary equivalent operator of a very concrete form acting on some spaces of analytic functions, and in our case this is exactly this space of Cauchy transforms, and so this is the function model. So let A, this is a compact normal operator, so we can think that this is simply multiplication operator, multiplication by z in L2, where in L2 of nu, where nu is this measure, this discrete measure. By Tn, I will always denote the inverse to this Sn. I assume that Sn is no zero, the kernel is trivial, for simplicity. And L is a rank 1 perturbation of A. Then there exist the following things. There exists a positive measure mu supported on this points Tn. So in other words, there exists a sequence of positive masses mu n with this property again that this series converges. There exists a space h of t mu generated by these two parameters for some choice of the function a, of course. And there exists an entire function g, such that the function g itself need not belong to our space, h of t mu. But it almost lies there, namely, it belongs to this class, h of t mu plus z h of t mu. So it's in the space up to a linear factor. If you divide, for example, g by anything z minus lambda, then you are in the space. Okay, and one more assumption that g of 0 is 1. So there exist such parameters such that our operator L is unitary equivalent to the following model operator which acts in the space h of t mu by the following simple formula. It's more or less like the backward shift, but we take f, we subtract something which give us 0 at 0 and divide by z, and this is a very, very explicit operator. Of course, all these functions of this g, mu, g, they are explicitly can be written in terms of these parameters a and b of our N-plan perturbation. I will not write down these formulas, but it's completely explicit. And conversely, of course, for any such an operator is a model for such some rank-1 perturbation. So these are exactly the same classes. So to study properties of rank-1 perturbations, one needs to study such very concrete operators, of this form, and this gives us all information. What are additional advantages of this functional model? Let's see. As here I mentioned that there are similar models were considered for rank-1 perturbations of unitary or self-adjoint operators under some additional restrictions, and there were some more recent results for finite rank perturbations developing this, but again, I'm not going into details here. What are the advantages of this model, of this operator? The advantage is that all spectral parameters of our operator L, they are mapped to some very concrete objects in our spaces. For example, the spectrum of L, it's obviously the inverse to the zeros of the function g, of this entire function g, parameter of our model, with Tn be its spectrum, then the spectrum of L are the points as said, which are one of Tn. Eigenfunctions of L, they correspond to the system of reproducing kernels. Corresponding kernels, of course, corresponding exactly to these points Tn of the zeros of g. And eigenfunctions, for example, of the adjoint operator, they correspond to the orthogonal system, to the reproducing kernels, which is given in a very explicit way. This is functions of this type, exactly those functions which appear in interpolation formulas. So all our questions about eigenvectors of our operator L can be restated in terms of reproducing kernels in the Cauchy branch spaces. For example, completeness in this eigenvectors. It corresponds to completeness of system reproducing kernels, which exactly means that we have a uniqueness set for the space H of T mu. Riesz bases of eigenvectors, they correspond to Riesz bases normalized reproducing kernels, and in its turn, it can be restated in terms of sampling and interpolating in the space. And spectral synthesis for L, it corresponds to the property that corresponding system reproducing kernels is what is called Strong-Markushevich basis, or also this property is known as hereditary completeness of a sequence of reproducing kernels. Let me just very briefly say what it means to be hereditarily complete. It means the following. So, just in an abstract setting, if you have a complete and minimal system in a Hilbert space, Xn, let Yn be its orthogonal system, and then we say that Xn is hereditarily complete if for any vector x in H, x is in the closed linear span of these vectors. Okay. And Marcos showed already quite a long time ago that the spectral synthesis for a compact operator is equivalent to this geometric property of the system of reproducing kernels, system of eigenvectors, that its eigenvectors and root vectors must be hereditarily complete. And for a system of reproducing kernels, this exactly means the following, that F belongs to the closed linear span of these summands, but what is in the product F with a reproducing kernel? That's exactly the value of the function at the point lambda. So, in a sense, it's a question whether our function F is not necessarily presented as a convergent interpolating series. The question is whether it is at least can be approximated by linear combination or finite linear combinations of the summands of its interpolation series. Okay, so how many time I have? or even 4. Okay, actually, I don't have much things to say, I'm afraid. So very briefly, well, so using this model, that's the key idea then of my talk. I don't have much time to present concrete results, but maybe it's not even. So the main idea then is that using this model, we can have many results about this rank 1 perturbations. Of course, perturbation theory, it's an enormous field. I don't know, 1,000, 10,000 papers that are very beautiful, important work. I mentioned here some classics and some more recent results. Still, there are always some restrictions. In more or less all results of this type, the perturbation is assumed to be small in comparison with our initial operator A. For example, there are so-called weak perturbations in the sense of Keldysh-Matsayev, where already we add to A something which is already a product of A with some, again, small compact operator or something. Then there are some variation of this, like p-domination, local p-domination. There are some interesting results about this by Mityagin, Shkarik, rather recent. Again, I'm not going into details here. And also another problem that in most of these results, it is assumed that unperturbed operator is self-adjoint, or at least normal, but it has spectrum situated on a finite number of rays. And the idea is that in our situation, we can get rid of most of these assumptions. We do not need to have weak perturbations. At least we can relax this very substantially. We do not need this information about location of the spectra. There are many results of this type, but maybe I will just. There are some results, some conditions. For example, in terms of the moments, one can give a condition about the completeness and spectral synthesis for such class of operators. There are many explicit results, which, as I say, are much better. Of course, the situation is very special, just rank 1 perturbation. But on the other hand, the results can be substantially better than in the general theory. But, as I already mentioned, the problem is, however, that still rank 1 perturbations already very complicated and large class, in a sense, because in general, all answers to all questions, they are always no. In general, we can have very bad situations, and for example, we can, for any compact normal operator, just without any restrictions, we can find a rank 1 perturbation, for example, such that, first of all, we can find a rank 1 perturbation which is not complete itself. We can find a rank 1 perturbation, for example, such that L itself has complete set of eigenvectors, but its adjoint does not have a complete set of eigenvectors, and the defect of this closure of the eigenvectors by E of L, I define this is a closed linear span of eigenvectors and root vectors is N. Also, we can find a rank 1 perturbation such that both of these operators L and its adjoint, they are complete. They have trivial kernels, but the operator doesn't admit spectral synthesis. There exist L-invariant subspaces. Such that the dimension of M minus EML. What is EML? By EML, I denote the set of exactly the part of my subspace, which we know from the spectral data. The closed span of root vectors, eigenvectors, which are in this space. And so we see that we always can have a very large part of our subspace M, which we do not know. This defect can be arbitrary number N and even infinity. Okay, then I think I will stop here. Thank you very much.